What if I told you that in the next few minutes we could work out what the derivatives of the 6 trigonometric functions and the inverse trigonometric functions should be using only what a first week calculus student might know? Let's remember how we define sine and cosine. Draw a radius on the unit circle. The y-coordinate or vertical coordinate of the point where that radius meets the circle is sine of theta, where theta is the angle subtended by the radius and the x-axis, and the x-coordinate is cosine theta. If we want to know the derivative of sine of theta, what we need to figure out is the change in sine over the change in theta for small values of theta. So let's change theta. When we do that, we get an extra little bit of angle delta theta, and the arc up there along the circle is also delta theta units long. That dotted vertical bit is how much sine changes. That dotted blue bit is how much cosine changes. Well, actually, how much cosine changes is negative, so the length of that blue bit is negative change in cosine theta. And we can create a right triangle by drawing in this little hypotenuse, which has length almost the same as delta theta. And because that little bit is almost tangent to the unit circle, we almost have two similar triangles here. So let's look at those almost similar triangles. If we want to know the change in sine over the change in theta, on the right side of the screen, we can take adjacent side over hypotenuse and get change in sine over approximately change in theta, but that should roughly equal on the left side of the screen adjacent over hypotenuse, which would be cosine over 1. So the derivative of sine should be cosine. If we look at the same picture but now take opposite over hypotenuse, on the right side of the screen we get negative change in cosine over change in theta, but that should be approximately equal to, on the left side of the screen, sine theta over 1. So multiplying both sides by negative 1, we get change in cosine over change in theta is approximately negative sine theta, so the derivative of cosine should be negative sine. If we draw two more line segments here, one that's tangent to the circle at x equals 1, and another a radial line segment making an angle theta with the positive x-axis that cuts through the circle, we can call the lengths of these line segments tangent theta because it just touches the circle, and secant theta because it cuts through the circle. Both of these are right triangles. Both of them share an angle theta. Therefore, they're similar triangles. And we can say that tangent theta over 1, opposite over adjacent on the right side, has to equal sine theta over cosine theta, opposite over adjacent on the left side. Similarly, secant over 1 has to be 1 over cosine theta. So this is how we define tangent theta and secant theta. If we change theta a little bit in this triangle, we get another little almost right triangle up there at the top. Here, the dotted vertical bit is the change in tangent, and that's the hypotenuse of this smaller triangle. The dotted radial bit outside the circle is change in secant, and that other dotted side along the circle has length approximately equal to delta theta times the radius of the circle, which in this case is secant theta. So if we take hypotenuse over adjacent here, we get change in tangent over change in theta times secant, and looking at hypotenuse over adjacent on the left side of the screen, we see that this should be approximately equal to secant theta over 1. So multiply both sides by secant theta, and you get change in tangent over change in theta is approximately secant squared, and we have the derivative of tangent is secant squared. Can we do the same thing for secant? Well, here let's take opposite over adjacent. So on the right side of the screen, we have change in secant over change in theta times secant theta. On the left side of the screen, this should be approximately equal to tangent theta over 1. Multiply both sides by secant, and you get that the derivative of secant should be secant times tangent. Can we do the same thing for cotangent and cosecant? Well, if we draw the proper triangle, we can, but I'll leave that up to you. Now, I first saw this technique in the preface of Tristan Needham's book, Visual Differential Geometry. But it's also in the preface of his book Visual Complex Analysis, which came out in 1999. He attributes his motivation to Isaac Newton's ideas in the Principia, although Newton never actually did what you've seen here. 10 years before Needham, Donald Hartig published an article in the American Mathematical Monthly where he used a similar geometric motivation to find the derivative of sine and indicates that you can do the same thing for cosine. Now, you might think that this geometric motivation for these derivatives is not all that rigorous. But as Hardig points out, the geometric arguments we use to work out the limits we need to compute these derivatives in the usual way, that's not really much more rigorous than the arguments we've used here in this video. If you want to be super rigorous, you can do what Michael Spivak does in his calculus book and define pi as a definite integral of the upper semicircle function, and then define a new function, a of x, using the same integral, and then define cosine as the inverse function of this integral function at x over 2, and then define sine in terms of cosine, and then you can work out all the properties of sine and cosine and all their derivatives and so forth using this definition. And that would be rigorous, but not something you're going to try during the first week of a calculus course. Let's return to our secant tangent triangle. We can see clearly from this triangle that secant squared theta should be 1 plus tangent squared. So if we write our approximation of the tangent derivative, we can replace secant squared theta with 1 plus tangent squared theta so that the tangent derivative is just expressed in terms of tangent. And we can do the same thing for secant as long as we make a proper domain restriction here. So looking at this new way of writing the approximate tangent derivative, let's take the reciprocal. Now, typically on the left there in the denominator, we would have change in a variable. So let's make tangent theta a new variable, t. That means that theta is the arctangent of t. So making this substitution, we have change in arctangent over change in t is approximately 1 over 1 plus t squared, and we have the derivative of the arctangent function. Can we do the same thing for inverse secant? Well, flip the fraction, make a substitution, there you go. Can we do the same thing for inverse sine? Here it is. We can do something similar for the inverse cofunctions, but we don't use those a lot, so I'll leave that to you. If you want to play around with some of these little triangles yourself, you can follow the link on the screen or in the description of this video to access an interactive Desmos graph. Thanks for watching, and let us know your thoughts in the comments.